Recording. Good morning and welcome back. We are today closing the unit 4, I believe, on electric machines and power converters. In the previous lecture, so today technically it's lecture 10, but in the previous lecture I had not quite finished describing the last topic, so I'm going to resume from where we left it off last time, which was permanent magnet synchronous machines. So if you remember, we had talked first about direct current machines, then we talked about AC, how AC machines work in general. We talked a little bit about synchronous machine, induction machines. Now we're going to focus on the permanent magnet synchronous machine that, as I think most of you understand, is the most common, most likely machine to be encountered in a electric or hybrid electric vehicle today. There was a brief conversation about Tesla a few minutes before class. It turns out that the original Tesla Roadster, the very first one, used an AC induction drive. And the AC induction drive that they used is a derivative of what we used to use in the 1990s to raise our Formula Lightning Smoking Buckeye when we were doing single-seater open-wheel electric car racing in the 1990s. From the next vehicle on, the Model S and on, Tesla then moved to permanent magnet machines. So the idea is that the permanent magnet synchronous machines have the advantage of having relative simplicity. The rotor does not need to have any windings. And the stator is the same stator I have described already, in which you generate a rotating electromagnetic field. So what happens here is that somehow you manage to generate a rotating electromagnetic field, and then the rotor, which contains permanent magnets, we will see how, follows along. Notice here rotary encoder. That is a position measurement device because it's very important in a permanent magnet synchronous machine to have a measurement of position. Let's see now if this is actually a video or not. Remember, I was able to make, yes. So you can see now that you have a stator. I'll use black here, and I'm going to put a lot of dots in it. These dots would be like the wires that are embedded in the stator. And the many wires that are in each slot may belong to each one of the three phases. There would be more for phase A, fewer for phases B and C in one slot, and then the other way around in another slot. In other words, there is a distribution. There is a distribution of wires that is appropriately arranged to try to give you something that is as close as possible to a sinusoidal flux distribution. Then you have, on the rotor side, permanent magnets. And in this picture, it looks as if you just have two permanent magnets and you have a north pole and a south pole, for example. So I'm going to run this simple animation that will show you how you have this rotating, assuming that it works. That was too much to hope for. All right, let me see if I exit. Cannot play media. Okay, somehow the movie is not in the right file. That's probably what we should do. Yuvraj, is find these movies, these videos, by the way, and put them in the same folder. But you have them. I'm almost sure, Daniela, you can check, but I'm almost sure that there are files that are videos. I don't know if they are, what kind of files they are, but it's some kind of a video file, AVI, MOV, something like that, in which you can actually play these animations and look at them. Now, this is a conceptual sketch of what the configuration of this machine might look like. What, in fact, it would look like, there are two typical interior permanent magnet machines. So here you would be bonding these magnets on the surface of the rotor. You know, if you're going to rotate at high speed, that's not a very good idea. So in the past, the development has been in the direction of so-called interior permanent magnets. And you can think of a couple of strategies. There is a third one that I will show you as well. These are plugs, you know, kind of chunks of magnetic material that are embedded in the rotor. That's one alternative. An alternative that has found favor, this is the Toyota Prius first generation, for example, is that you embed just a slit near the surface embedded in the material of which the rotor is made, which is a ferromagnetic material. You embed this permanent magnet, and you say, gosh, this is a much smaller than that. Yes, because that's a little slice of permanent magnet that is built inside the rotor is in fact a rare earth, very high coercivity permanent magnet, so that you actually get a lot of action in a relatively small mass and volume. So those are two configurations. And here now is a map, torque speed map, of an electric machine that we considered using in one of our competitions many years ago. This is probably 15 years ago or so, but the technology is similar to what is being done today. Of course, these things always improve, but I want to illustrate to you some of the characteristics that you would think about in considering an electric machine for an application. This map was generated under specified test conditions. There are two cases. One is continuous output, two is peak output. Continuous output describes itself. This basically means the machine is generating output power continuously. 300 volts DC and, very important, 55 degrees C coolant. You need to cool the machine at 55 degrees C so that as you produce heat during operation of the machine, this heat is appropriately dissipated on a continuous basis, and you can produce that output continuously without exceeding any temperatures that would be undesirable in the machine. Small parenthetic comment. Permanent magnets all have a critical temperature above which they demagnetize. That temperature is much higher than 55 degrees C, but remember that 55 is the temperature of the coolant. The machine itself will get warmer than that. So that's continuous output. When you look at this machine in a continuous output mode, you notice that it will put out something like 550 newton meters of torque. It has a corner speed of about 550, this is radians per second, not RPM, okay? And you notice that it does this usual thing that we've talked about. You have a constant power region here, and you have a constant torque. Now, this machine was developed for hybrid electric vehicle applications. But if we were for an electric vehicle application, this would have to be a small car, because continuous output of 30 kilowatts would not be enough to keep a full-size automobile going at 70 miles per hour on the freeway. But a small car would be okay. However, this was designed for a hybrid electric vehicle. In a hybrid electric vehicle, you don't really need continuous power output. Because, yes, the machine may be used frequently, but it's not outputting continuous power. It tends to do it in bursts. It'll help you to provide some acceleration when you start from a lower speed. It'll help you when you brake to recover energy through regenerative braking. It'll do all these wonderful things, but the bursts of peak power are relatively short. So here is a description of how this machine is capable of generating a peak output, same bus voltage, same coolant temperature, but the duration is 45 to 60 seconds. What this doesn't say is after you have exercised the machine at that peak power for 45 to 60 seconds, then you have to keep it off for a while because you need to bring the temperature down again. Okay, so if you can think what the duty cycle is, I don't know, but you can think of a 50% duty cycle. If you exercise the machine at its maximum power for 60 seconds, probably you should let it rest for 60 seconds. And maybe that's not necessarily one-to-one relationship, but that's just an illustration. You can think of it as an athlete in a sport like, for example, soccer or football or basketball. They don't sprint all the time. When they do, they work really hard, but they can't be sprinting for 90 minutes of a soccer game. No way they can do that. They can trot, run, and sprint in appropriate proportions. So if I now look at the peak output, which is going to be in blue now, notice that this machine is capable of generating, for a short duration of time, 2.5 times the continuous power output. And depending on what cooling system you put on the machine, who knows, you might be able to do more. But if you think in the back of your mind, whenever you have an electric machine, that its intermittent rating is approximately twice the continuous rating, that's a reasonable approximation that you can always count on. So this is a machine that can produce as much as 1,700 Newton meters of torque, and of course a continuous power of 75 kilowatts, continuous power, peak power, for a short duration of time. In a hybrid electric vehicle, you can typically elect to choose a smaller electric machine, knowing that you can push it to 2+ times its rated power and torque for short periods of time. Yuvraj has a question.
So if we take the continuous output map instead of peak output map for an optimization algorithm, because continuous output can give me continuous output, then does that mean that my control strategy that I get from that algorithm is suboptimal?
So this is a very sophisticated question, because it talks about how would you optimize an energy management strategy. So Yuvraj is only about 6 weeks ahead of, or 7 weeks ahead of the class with this question. But the idea is, if you're trying to decide the optimal way of utilizing this electric machine, you will get two different answers. Depending on whether you say, oh, this is a 30 kilowatt machine, I'm going to use that and the red torque curve for my optimization algorithm. Or you could say, what would happen if I use this other curve, 75 kilowatts, and solve the same optimization algorithm, which gives you an answer of how much do you use the electric machine, how much do you use the combustion engine. You will get two different answers. And Yuvraj, neither of them is optimal, because to actually arrive at the optimal answer, you would have to somehow build into your optimization algorithm an understanding of how you're going to use the electric machine, for how long, right? So if you knew that over the next 30-second time window you need the electric machine, you have available 75 kilowatts. If, on the other hand, the maneuver requires that the electric machine operates over a span of a few minutes, then you would have to use the other value. So your question is very good, and it's not an easy answer. But I'll tell you what we have done in a recent project. We solved this problem. Vijay probably knows. And what we did, we used a continuous rating, because even though you could do better probably by using a mix of continuous and peak rating, if you use the continuous rating, you're going to have a conservative answer that will never get you into trouble with overheating. It will not be the optimal answer. Your outcome will not be quite as good as it could have been. Good question. So one of the other things that is also done is now that these interior permanent magnet may, instead of looking just like a simple bar like this, they may have a slightly more complicated shape, where they're not just a flat line, but they actually curve up at the edges, and I will explain why in a moment. So generally speaking, a permanent magnet synchronous machine has almost zero rotor losses. There are no wires, so there is no current that is going to generate heat. It has pretty high efficiency across the board. It's easier to cool, because this is another important consideration. Since you don't have wires in the rotor, you're not generating heat in the rotor. So the cooling of it is easier. You're only cooling the outside, the stator. Generally speaking, it'll be smaller by volume and mass both. It means lower inertia. Lower inertia means that it's easier to go at higher speeds. Since power is the product of torque and speed, and torque is proportional to the volume of the machine, to the volume of the rotor. If you go to higher speed, you can make a smaller machine. So one approach to improving the packaging in a permanent magnet synchronous machine is to go to higher speed so that your power requirements are met with a much smaller machine package. Of course, lower torque may require that you deal with gearing in a different way, of course. So here's an example of the improvement between the first generation, so Gen 1 of the Toyota Prius had this configuration with this slabs of ferromagnetic material, of rare earth magnet, and the second generation, Gen 2, on the other hand, had them configured in a slightly different shape. What Toyota was able to do in going from hybrid system 1 to hybrid system 2 was to first of all improve the torque, you can see, and even more significantly, improve the output power from 33 to 50 kilowatts, and this is really significant. And this was accomplished by a combination of electric machine design. The torque improvement is actually caused by this, and I'll explain why. And the power improvement is caused in part, if you increase torque, you will increase power. But in addition to that, they reduce losses by doing something with the power converter, which I will describe to you later in today's lecture. So, having explained the big picture of all of these different types of electric machines, the traditional DC machine with brushes and commutator has some very clear advantages. It's simple, easy to control, but the reality is that it requires maintenance. You know, remember, you have to change the brushes, and it's low efficiency, low speed range. You can have arcing, which is not a good idea. By the way, for those of you who are interested in learning more about it, this is a fantastic article in the IEEE Transactions on Vehicular Technology. It's not that old, 2012, which is actually explains all of the trade-offs among all these different technologies. Very well done. The induction machine is a good solution. Generally speaking, it's not as efficient as a permanent magnet synchronous machine. Depending on what the application is, it may be that the induction machine is preferred, maybe. The PM synchronous machine is the one that today is used most commonly. It has the highest power density, doesn't have rotor losses for practical purposes, and you know, it's a good machine. Also, it tends to work well both as a motor and as a generator. The induction machine can operate as a generator, but it's relatively low efficiency. So you still can do braking regeneration with an induction machine. Every electric machine can act as both motor and generator. And then I briefly mentioned the existence of these switch reluctance machines. I will not describe them in this lecture. They are really not, they've not found a place in the commercial market. One of the things that I wanted to illustrate here qualitatively, I don't want to go into the specifics, but you can read, this is the same paper that I just mentioned a minute ago. I want to show you the following point. There are different machines here. This is A is a surface-mounted permanent magnet, B is an interior permanent magnet, C is an induction machine. I'll just stop with these three because we've talked about them. What I want to point out is that as you design these machines, while the torque speed curves are similar, they all more or less look the same. They have some kind of a constant torque region and a constant power region. Where the ISO efficiency contours are actually depends on the machine design. So you can see that this machine has its highest efficiency there. This one has the highest efficiency here. They're two different places, okay? And here's another one. This machine has its highest efficiency point to maximum power. That probably wouldn't be good for an automotive application because how often do you really go to maximum power, okay? So similar, the same is true of this other machine design. So anyways, read that paper if you're curious. And I will say a couple more words about, in general, some of the design criteria that go into deciding how to design an electric machine, because there isn't a single recipe. There are trade-offs, and the trade-offs involve the mechanical structure. Radial versus axial flux machine. Typically, you have a radial flux machine. Every electric machine you're likely to have seen is a radial flux machine, but axial flux machines also exist. And you can see here what the difference is the direction in which the flux, magnetic flux goes. So the mechanical structure also is important for noise and vibrations purposes, strength and weight. There are many different criteria. Then you're going to have to determine the electromechanical specifications. For example, ratings, torque per unit rotor volume. That has to do with the torque density of the machine, right? How much torque per unit rotor volume? That's, of course, going to do with how you configure the windings and what materials you use, for example, for the permanent magnet. Cooling, well, that's so important. Are you going to have natural convection, forced convection, ventilation, water jacket, spray cooling? You can use both water and oil-cooled machines. And you have to worry about the magnet and winding thermal properties. So I mentioned that there is a critical temperature for every permanent magnet. If you exceed that temperature, the magnet becomes demagnetized, and you just threw away a whole bunch of money down the drain because that magnet is done. There's nothing else you can do about it. But temperature has an effect also potentially on the wire insulation. So you also have to be sure that the electrical insulation you use on the windings, which by definition you want it to be very thin, right? It's a coating. It's almost like a really fine, thin coat of paint on the wire, okay? Well, if that insulation somehow degrades because of high temperature, you'll have short circuits. Don't have short circuits in electric machines if you can avoid it. It's not a good idea. Okay. And then, finally, how do you control it? And that's a whole other world, but we'll talk a little bit about that in the remaining part of this lecture when we go to the electric drive systems. So we're interested in maximum torque. These are some of the things that you are interested in. The rated speed. Rated speed is also called the corner speed. It's where you go from constant torque to constant power. Efficiency, of course, we're interested in that. And it's the efficiency of an electric machine doesn't depend only on the electric machine design. It depends also on how you control it. So I will now give you a brief review. We'll go back to the Willans line ideas that we have already reviewed for the internal combustion engine. And I'm going to say, look, we can represent an electric machine using a Willans line just like we did an internal combustion engine. You have this input power, you have an output power, and you're going to have some losses. So if the losses are represented by the y-intercept relative to the output power, a negative number, and this is the input power, your Willans line is defined by a slope, a coefficient E, which is the intrinsic energy efficiency of the machine, and by some power losses. E and P loss are not constant. We already know that. They're going to be functions of speed and load. So I can write that the output power, mechanical power, is the product of torque times speed. But that's equal to an efficiency, eta, times the input power. And the input power is voltage times current. So the efficiency of the machine, eta, which is the output power of the input power, is going to be equal to the intrinsic energy efficiency of the machine minus the other losses, things that have to do with friction and aerodynamic losses, and in an electric machine, core losses, the magnetic losses, okay? And that's going to be P loss divided by P in. So E is the maximum efficiency that you can get, and eta is the actual efficiency of the machine. So that explains very clearly the relationship between eta, the efficiency of the machine, and E, the actual efficiency, and E, the intrinsic efficiency. So in internal combustion engines, we saw that there are two normalization factors. We define a mean effective pressure by dividing the work the engine can do by the volume, displacement volume of the engine. So that when you talk about an engine that has a mean effective pressure of whatever, 15 bar, it doesn't matter if the engine is a 1 liter, a 2 liter, or a 3 liter engine. We've normalized. Second, in an internal combustion engine, we said, look, the mean piston speed, the average speed of the piston as it travels up and down, is a variable that normalizes the RPM regardless of what configuration the engine is. You could have a tiny engine like in a model airplane that can rev a really high RPM, sounds like a bee when it flies around, or you can have a big ship diesel engine that moves very slowly. If you look at the mean piston speed, you end up having variables that are comparable. What do we do in an electric machine? Well, it turns out that if you look at something that is called by electric machine designers the air gap shear stress. What's that? That's the mean force acting on the rotor divided by the area of the rotor surface. So here it is. It's essentially the force that causes the rotor to move. So that's the air gap shear stress. And you can obtain it by essentially doing the same thing that we did with internal combustion engines. We use the rotor volume as a normalization factor. If I normalize by rotor volume, the air gap shear stress of a small machine would become comparable to that of a large machine. That's pretty easy. Second, we now have a second variable that we use for normalization. In the scale speed is the tangential speed at the rotor surface. So in an electric machine, what we're doing is we're looking at what happens at the rotor surface. What is the air gap shear stress, the force acting at the rotor surface, and what is the tangential velocity at the rotor surface? Those normalize the difference in shape of different machines. And so C sub m is going to be equal to r, the radius of the rotor, times omega. So in short, for electric machines that are in the same class, they have to be similar. The same way you cannot compare a gasoline engine that is naturally aspirated with one that is turbocharged, or a diesel engine with a gasoline engine. Similarly, if you have a surface permanent magnet machine versus an interior permanent magnet versus an induction machine, all of those are different manifestations, and in each of those classes you can then use this normalization. And the normalization factor becomes the rotor volume for the mean effective pressure and the radius so that you can arrive at a tangential velocity at the rotor. So now, in writing the expression P out is equal to an efficiency E times PA, remember that available mean effective pressure we had talked about, minus P loss, the mechanical losses and magnetic losses, we can then define the mean available pressure. This is the theoretical work that the motor could do if there were no losses in it, right? And it's equal to VI, the electrical power, divided by omega, and then it's normalized by the rotor volume. On the other hand, the mean pressure losses are going to be the actual pressure losses normalized again in the same fashion by the rotor volume. And, as I said already, the velocity is normalized this way. Again, you can express E and PML as polynomial functions. doesn't have to be a polynomial, but that happens to be an easy way of doing it. And we express them, careful here, we express them as polynomial functions of the mean velocity, okay? That's what we're going to use, the normalized velocity. So I'm going to show you an example now. We're going to take a 32 kilowatt permanent magnet machine on which we know torque, speed, and efficiency curves, and we are going to develop a Willen's line for it. So first of all, I'll make a few observations. Electric machines have much lower mean effective pressure and much higher speed than internal combustion engines. So the engine produces more, quote, normalized torque, but at a lower speed. The electric machine has a lower, quote, normalized torque, but it does it at higher values of C sub m. Also, this is very important, electric machines have a value of E that is greater than 0.9. The intrinsic efficiency of an electric machine is better than 90%. Then you have to cope with the losses, okay, with the core losses, magnetic and mechanical losses. Okay. So let's take a look and see what happens. And what I'm going to do also in the next couple of slides is to show you a comparison of what the coefficients E and PML look like internal combustion engine compared to electric machine. So first of all, that's an efficiency data that we had for some 32 kilowatt permanent magnet synchronous machine. And here is the Willen's line fit where you have PME here. This is the available mean effective pressure, and this is the mean rotor speed. You can see that where the dots are the actual data and the magenta line is the curve fit, it is just about perfect. It really works quite well. Similarly, here is another example. This is an 83 kilowatt AC induction machine. So what we learned from this is that in fact the Willen's line that was developed by Mr. Willen's a century and a half ago for combustion processes, not just internal combustion engines, but combustion processes. It could be a furnace, for example. That Willen's line is in fact, it works even better for electric machines. And here's what I promised. I'm going to show you a comparison of E. So this is the intrinsic efficiency as a function of C sub m, of mean speed, right? The horizontal axis is the mean normalized speed, mean rotor speed. And here it is, E for an internal combustion engine, and E for an electric machine. Look what happens. In an internal combustion engine, you have E that has a peak somewhere in the middle of the speed range and goes from values that may be, let's say, 0.4 to 0.5. Now, you know that 40 to 50% efficiency for an internal combustion engine would be really excellent if you could achieve that. But you don't, because the efficiency, actual efficiency, is not E. You have to deal with the mean pressure losses. And the mean pressure losses, which are friction and pumping in an engine, they're the aerodynamic gas flow losses, and, of course, the friction, piston and ring friction, crankshaft bearing friction. Those are significant. So the PML, if I measure it in Pascal for an internal combustion engine, so this is PML for the internal combustion engine, notice the units here. This is 250 kilopascal is the peak. Okay. Let's now take a look at the electric machine. In an electric machine, I am roughly, let me generically say, 0.8 to 0.9 is the value of E. Not only that, but in addition to that, PML in the electric machine is very low. The peak value here is 250, not kilopascals, pascals. So the losses in an electric machine, those mean pressure losses, are 3 orders of magnitude smaller than the internal combustion engine. You don't have the flow losses and all of those. Imagine, think about piston and ring friction. You're continuously rubbing these rings against the cylinder walls in an engine. I mean, no matter how good your lubricant is, there is friction there, right? So that's fundamentally, in the Willands line world, how things look for internal combustion engines versus electric machines. And these are now examples of scaling. Now what we did is we said, okay, let's take a 2.5 liter diesel engine, or rather, let's start with a 1.9 liter engine, and let's scale it up and see what happens if we make a 2.5 liter diesel engine. At the time when we did this, VW and Audi were not quite exactly the same company, the same way they are today. Doesn't matter though. The point is that if you take a 1.9 liter diesel engine, scale it up to 2.5, and then compare that scaled up with an actual 2.5 diesel engine, it looks pretty good. Okay. And this is, on the other hand, a 25 kilowatt AC induction machine scaled from an 83 kilowatt machine. So we take the parameters from the previous 83 kilowatt machine, scale them down to 25 kilowatts, compare with data that we have for a 25 kilowatt induction machine, and again, the results are quite good. So as long as you remain within a family of machines, internal combustion engines or electric machines, the scaling that you can do is actually quite effective. It works through the Willands line. That is the end of Lecture 9, Overview of Electric Machines, and what I'm going to do is keep going now with what I was supposed to start at the beginning of this lecture, which is Lecture 10. So, electric machines are great. They look wonderful. High efficiency, relatively compact, but you have to control them. Somehow you have to be able to supply three-phase voltages to generate three-phase currents, and you have to do it in a variable frequency world, because you remember that the mechanical speed of rotation of an electric machine is dependent on two things: the frequency of the electrical power supply and the number of poles, which is the design, the construction of the machine. When you know those two things, the number of poles and the frequency, you know the speed of rotation of the machine. But an electric machine that is used today in an actual application is a machine that could easily have rotational speeds that go from 0 to 10,000 RPM. That would not be uncommon. In fact, in an effort to make this machine smaller and smaller, remember what I said, high speed is better for packaging? Today, there is talk about pushing the 20,000 RPM range for these machines, because you can make them a lot smaller. And the reason you can get away with it is because the losses that are associated with rotational speed, while they're significant in an internal combustion engine, where you want the internal combustion engine to actually operate at lower speed to reduce friction losses, in an electric machine, as I just showed you from the numbers you saw, it really doesn't matter that much. There isn't an awful lot of loss related pertaining to the speed of rotation. But you have to control them. How in the world do you make three-phase sine waves from DC currents? If you haven't thought about it before, this should kind of challenge you, because DC means constant. AC means sinusoidal. How do I make a sine wave from a constant current? Well, that's done by electric drives. Here's a picture. This is an early generation Ford Escape hybrid. And in this particular generation, this is 10, 15 years ago, you have the electric machine and you have the power converter, and you can see that they're two separate units. So you need to have high voltage orange cables. The EcoCar team understands orange cables very well. And that's not good. Today, the push is towards integrating these things into one package as much as possible. So let's talk about power converters in general. Given that there are two types of electric power, Edison versus Westinghouse, DC and AC, okay? You have four possible ways in which you can convert power. DC to AC, which is what we want to do. You want to start from DC power and turn it into AC, alternating current. Those devices are called inverters. They're triple important. Without those, you can't have AC machines or AC drives. Then you have DC to DC converters. When we talk about some of the improvements Toyota made in first to second generation hybrid system, it will turn out that they made very good use of a DC to DC converter to increase the voltage of the battery pack from like 250 volts to 500 volts. Those are not the exact numbers, but to give you the rough idea. So DC to DC converter is also very important. So one function is to say, I have a battery pack that is 250 volts. How about if through electronics I make that 500 volts? If I find a way to do that, I double the voltage, I cut the current in half. But if I cut the current in half, what do the I squared R losses do? They're cut into 1/4, right? Because it's I squared. So higher voltage is a really good idea if you can get away with it. Toyota did it through a DC to DC converter. I will explain that when we talk about that Toyota hybrid system. There is another very practical application of DC to DC converters in electric vehicles. You still have things like infotainment system, headlights, interior lights, dashboard functions that run on 12 volts. So in a hybrid electric car or in an electric car, you still need a 12-volt DC power supply. Now, you could have a separate 12-volt battery, or you could use a DC to DC converter to take your 400-volt battery pack and some of it, through a DC to DC converter, step it down to 12 volts. Those are the two important functions. I want to make, let me make a side comment here, okay? Could you, is an AC to DC converter important? What do we call it? A rectifier. AC to DC is a rectifier. Is there a rectifier in every automobile in the world? Pretty close, because if you have an alternator that charges your battery, alternator gives you AC power output, you need to rectify to get a DC current to charge the battery. So this is in every car. That's another triple check. Okay. There is another thing, I'll put it in parentheses, that is called an AC to AC converter, in which you might say, oh, I have a device that operates at 60 hertz, but I want to make it operate at 50 hertz. So can I take a 60 hertz power supply and turn the sine wave into a 50 hertz sine wave? Does that sound complicated or what? It is, actually. There are cycle converters that will do that, but thankfully we don't have to worry about that. There's no application that I can think of that would be of interest to us. But the other three are important. And really, inverters and DC to DC converters are the most important ones. Now let's think about it in terms of a drive. What's an electric drive? An electric drive is the combination of a power converter plus an electric machine, which of course has a power supply somewhere. So in a car, there would be a battery, power converter, electric machine. The current that is generated in this electric drive could fall into one of four quadrants. For example, if the current is current and voltage, the power, if the current and voltage are both positive, that means that you're producing torque with the electric machine and you're motoring, moving forward. If both current and voltage are negative, the power is still positive, meaning that I am transferring positive power from the electric drive to the wheels. So it's still motoring, but that means I'm in reverse. So if I flip the polarity of voltage and current, I have reverse. So, by the way, in electric cars, in principle, you don't need mechanical reverse. You can do it electromechanically. I used to joke when we had our electric race car that there was nothing that would stop our electric race car back in the 90s, which had a top speed of probably 150 miles per hour. There was absolutely nothing that would prevent it from going 150 miles per hour in reverse. Because all you have to do is reverse the field and boom, you go in reverse. Now, steering could present some challenges. If you've ever thought about rear wheel steering, which is what you would have to do, never mind the fact that you're looking that way and going backward. But anyway, so we never tried that, but in principle you could. On the other hand now, if the voltage is still positive, but you reverse the direction of the current, we call that generation. That's forward braking, and it's the regeneration. That's what you do when you want to recover electric power and recharge the battery upon braking. Similarly, if you somehow are doing 150 miles per hour in reverse, then you could also regenerate in reverse. I don't recommend it. Don't do this at home, okay? So what we're going to need if we have an AC machine are going to be variable frequency drives. And a variable frequency drive is typically configured in different ways depending on what the source is. I'm going to cut to the chase here and go directly to an electric car, right? Because I'm going to have a DC source, a battery, right? In a industrial application, I wouldn't use a battery. I would go to my three-phase power supply from the electric power company, and I would have to rectify that to get DC here. We then have something that is called the DC link, which in its simplest form is just a pair of wires, right? But this is the DC link, and this is the DC link voltage is very important. The battery is what determines the DC link voltage in an electric car. Then you're going to have this device that is called an inverter that takes these DC voltages and currents and turns them into alternating currents. And there is a controller that makes it operate. And finally, you have a three-phase motor where you're going to have your A, B, C phases, and each of the currents in the A, B, C phases are going to be sinusoidal. So ABC, you have sinusoidal currents here, whereas at the DC link, you're going to have DC plus minus, and these are DC currents. Okay. How do you do this? Well, I'm going to construct a very inexpensive and incredibly simple inverter for you. First of all, I buy a battery pack. And I get inside my battery pack and say, let me make a connection here, an electrical connection in the middle. So essentially, I have divided my battery pack into two battery packs, V sub S over 2 and V sub S over 2. And I put a reference point, what I would consider ground in my circuit, right in the middle. To this ground, I connect my load, what I wish to receive power from. Then I go to the supermarket, maybe not to the supermarket, Radio Shack if it exists anymore, and buy two electronic power switches. What are these electronic power switches? For example, they could be insulated gate bipolar transistors. Ever heard of those? Some of you may have IGBTs, okay. They are electronic devices which, when given an input signal, they become practically a short circuit and conduct current. When given another input signal, they become an open circuit. So it's a 1-0, it's a switch. If the power level is lower, you could do it with MOSFETs too. Okay. So what do you do here? How does this work? Well, let's imagine now that I have created a short circuit here by closing switch number 1. Okay. Oh, and by the way, I also have to buy a couple of diodes. I need these diodes. Remember how diodes work? They only conduct current in one direction. Okay. So what's going to happen here is if this battery tried to put some current out, I'm going to do a dashed line, it can't go that way. It cannot find the closed circuit because the switch is open. That's an open circuit. So it's going to keep trying. Can it go this way? Well, it could try, but it won't be able to do that either because that diode is reversed, so it cannot conduct current. So when the switch is closed, this source is not doing anything. On the other hand, this V sub S over 2 is allowed to send current flowing in this direction. I want to point out that when switch S1 is closed, the current is going to flow from right to left through the load. Now, let's reverse the situation. Now, let's allow for the fact, I'll use a different color. Let's go to this blue color here. Let me first erase this. Now I'm going to reverse the situation, and I will open this switch and close this one. The situation now is reversed because current coming from this supply is actually capable of closing a circuit and traveling this way. And look at what just happened. When switch S1 is closed, I have current flowing from right to left. When switch S2 is closed, I have current flowing from left to right. So by operating the switches, okay, flip-flopping between the two of them, what I've actually done by turning the switches on and off, so this is the current that I get from switch S1, this is what happens when I have switch S2 on, I have effectively generated a square wave voltage. Okay, square wave voltage. So now you say, wait a minute, you told us that we wanted sinusoidal currents. You made a square wave current. Well, it turns out that we have an alternating current. Let's put it that way. We agree that it's alternating. Yuvraj, you have a question?
So that these switches is very critical because if the switches are not able to synchronize themselves like a CAM mechanism or something, then I potentially have a short circuit.
Right. So another very good question, Yuvraj. That is exactly right, and that's why we have diodes D1 and D2. The presence, they're called flywheel or freewheeling diodes. They're critical. Without those diodes, if you didn't synchronize the switching on and off to absolute perfection, you could have a short circuit and blow up your converter. So those diodes prevent that from happening. I'm not going to explain it here, okay? But chapter 12 maybe or 13 of my book covers that. So if you're really curious to see the details, but these diodes are very important. They are life-preserving diodes. Okay. Now, I want to make another point. What's the load going to look like? What's my load? What type of device is it? What's an electric machine made up of? I am providing current to the windings of an electric machine. What are the windings of an electric machine? It's an inductor, it's a coil. So my load has an inductance in it. Is it possible that the wire also has resistance? Why not? I mean, if you can find something that has zero resistance, let me know. We'll make money together. Okay. So you have an RL load. That's what the load looks like. So what happens now, for those of you who remember system dynamics, first order systems and the like, if the voltage is a square wave, you know that the current is going to be exponential, right? And what it looks like exactly depends on the time constant, right? Which is L over R is the time constant, right? Okay. So what's going to happen now is that, in fact, the current is not exactly sinusoidal, but it's not as ugly as a square wave. It's a little better than that. Okay, so I would not quite be ready to turn this into a commercial product. It's very crude. And there is one improvement I can make immediately. I said, look, what if I were willing to spend a little bit more money now and buy, instead of 2 switches, I'll buy 4 switches and 4 diodes. Now I would have a situation in which I could use a single voltage source, and when switches S1 and S2 are closed, I would have a current that flows this way. So you can see that it would go through the load from left to right, plus to minus. If, on the other hand, I now close switches S3 and S4, my current would flow this way, and naturally it would flow in the opposite, it would flow this way, which means it would flow in the opposite direction. Very similar to what I just described, except that now instead of going from plus V sub S over 2 to minus V sub S over 2, I have doubled the voltage range, which is a good idea. But what about 3-phase? You know, that still is a single-phase inverter, single phase. I only have one AC waveform. Okay. Well, if I now have 3 windings to connect to, these are my 3 loads. Remember, each load is an inductor resistor. Okay? Now I have these 3 loads. What's going to happen is that I can now, by having the appropriate switching sequence, I can use switches S1 through S6, okay? 1 and 2 work together during one switching, 3 and 4 work together, and 5 and 6 work together. There are different ways of switching. The switching strategy is a little bit more complicated. And in the end, what you would get are phase voltages that would look like that. And the currents also look like exponential-like things. So I hope that I have convinced you. This is a little bit like convincing you that there is a rotating electromagnetic field. You really couldn't see it. You had to believe me, okay? Similarly here, I'm telling you that it is possible to generate AC waveforms from DC waveform using this switching approach. And in reality, the way you switch these switches is not the way I have described it, by simple big square waves. You actually use a technology called sinusoidal pulse width modulation, in which you're actually switching the switches a lot of times, and you are creating in the switching, this is a really simple example, but I approximated this. Look at what happens. The switching time is maximum in the middle, a little less here, and even smaller here. In other words, I'm approximating with the switching something that it looks like a sine wave when I integrate it, if I were to integrate this. Now, I showed you 5 pulses here. In a real PWM switching application, you wouldn't have 5 pulses to do half a cycle of a sine wave. You might use 500, so that the approximation of the sine wave is quite good. And here is a 1990s vintage homework assignments for students in EC 743, which was the class on electric drives. Design a switching sequence that has the least amount of harmonics, that is the closest to a sine wave. So you have to do Fourier analysis to death, okay? And back in those days, the students did that stuff by hand. Fortunately for you today, you can go buy a chip that does that. You don't even have to wonder what's inside it, okay? Someone figured that out for you and put it on silicon for you, okay? So the idea then is that the controller includes a chip that does sinusoidal PWM modulation, and so it'll switch these switches in an appropriate way so that they generate something that is as close as possible to a sine wave. Now, what do you think? Will there be harmonics? Yeah, I think it's impossible to imagine that you have on-off switches and don't have any harmonics. You can minimize the harmonic content, but one of the unfortunate consequences of this behavior where you have switching, PWM switching inverters, is that you're going to have electromagnetic interference. You're going to be generating higher frequency harmonics, which could then couple to your signal circuits and cause noise. So noise generated by high frequency switching in inverters is something that you have to protect against. Some of it will be there. You try to minimize it, and then after you've done your best to minimize, you shield, ground, do all of these things that you can do to clean up the circuits. This imperfect picture here, these devices here are actually pictures of IGBTs, but we forgot to put the arrow in them. So those are the switches with their diodes, and you can see here that they're very explicitly connected to an electric machine. So if this is phase A of the electric machine, the windings of that electric machine have an inductance, they have a resistance. What's this? Why is there a voltage source inside? What's that called? Back EMF, thank you. Just like we had a back electromotive force in DC machines, Faraday is Faraday. I mean, he was right. So that applies to AC machines as well. So you're going to have a back EMF inside AC machines as well. The way we control these operation, because now you have to control this, is done. There are many approaches. I'm going to explain the very basic idea behind field-oriented control. How many of you have ever heard the expression field-oriented control? A few people, okay, not many. Let me explain it. I have a DC voltage source. So this is my power supply, my battery. So here I'm going to have a DC current. Okay. Obviously, plus, minus. Okay. Then I have the inverter. What's the inverter going to do? Well, the inverter is going to give me 3 AC current. So it's going to give me I sub A, I sub B, I sub C. And these are all sinusoidal. And I just explained to you how we make them sinusoidal. In fact, what causes the inverter to generate these sinusoidal currents and voltages is a PWM generator. PWM generator. How many arrows are going into the inverter? You can count them, but you also knew this already. How many switches do I have? 6, because I have 3 phases, 2 switches per phase. So I have 6 of these switches, and each of them is being furiously pulse width modulated, vigorously pulse width modulated, okay, to generate sinusoidal currents. Following me so far? Okay. Now I bring back the subject I explained when I talked about how do we control DC machines. Do you remember that in DC machines we had 2 different things that we controlled, the flux and the torque? The torque was controlled with the armature windings. That was one of the 2 accelerator pedals, right? And the flux is controlled with the field winding, and that was the other accelerator pedal. It turns out that over the years, people figured out that if you want to control an AC machine, and if you can do a transformation from 3 phases, so 3 distinct axes, A, B, C, to 2 phases, called D and Q, where D stands for direct and Q stands for quadrature. Quadrature means orthogonal, right? Perpendicular, so 2 independent things. The idea is that you take the 3 phases of the electric machine and convert them into 2 phases, which you want to control as if they were independent control of flux and torque. So what we do with AC machines in field-oriented control is essentially imitating what we already know how to do with DC machines. That's how it works. We basically try to have 2 independent, distinct controls, one of which says, I'm going to set the flux to some value I like. For example, at high speed, I want to reduce the flux to reduce the back EMF. And the other one is, that's torque control. That's your torque accelerator pedal. So there is a set of transformations, a pair of transformations that are called Park and Clark, from the name of two people, which are trigonometric transformations that take you from 3 currents to 2, from ABC to DQ. Now remember that you can do this in a unique fashion, because if you have the 3 currents are related to one another by the phase, so if you know 2 of them, the third is already automatically determined. So you haven't lost any information in going from this mapping from 3 currents to 2 currents. Now you are in a new world. The new world is one in which you have IQ and ID current. And you now set your reference values. You say, oh, I would like IQ to be a certain value, IQ star, and in this particular case, oftentimes it's okay to set one of the other value to 0. You can do that. And so basically you now say, I have reference desired values for ID and IQ, which are really related to my torque and flux. And what I'm going to do is measure the ID and IQ. I actually don't measure ID and IQ. I measure IA, IB, and IC, and then I do a conversion, just a trigonometric conversion, okay? And I compare those with the desired values, and I have some kind of a PI, proportional integral controller, okay, to bring that error to 0. It's basically garden variety undergraduate PID control, okay? There's nothing exciting about it. And you're controlling 2 variables, the Q current and the D current. You also have to set your reference values. What do you want them to be? So somewhere else, there is another table that says, under these conditions, I want this value for ID and IQ and so on. When you are done with this, you are going to go into, you're going to take the value, oh, so you have an error now, right? Because the difference between the desired value and the measured value is the driver for the controller, and that's going to drive your PWM generator and change the frequency and magnitude of these voltages and currents as you need. So that's how you do the basic control, field-oriented control of an electric drive. If you really, really wanted to learn how to do this, there is a class that is taught in ECE that includes a lab. And over the years, some of my mechanical engineering graduate students have chosen to take that class because they really wanted to learn this, because they were doing research in depth in, for example, diagnostics of electric drives, so they needed to understand how it worked. It's a great class. If you're really passionate about electric drives and you think that that's a future career, don't let the fact that you're a mechanical engineer slow you down. Anyone can learn this if you want to. There is nothing that special about it. Now that you have that power converter and motor controller, that would be this part, you also need to satisfy other functions to make an electric drive work fully and completely in your system, because you have a high voltage system. This high voltage system is the battery, 300-400 volts. If you look at commercial vehicles, you could go up to 600, 700, even 800 volts. The Buckeye Bullet runs at 1,000 volts nominally. So you also need a battery management system, BMS, or battery energy management system. So when we speak of batteries, which is the next module, I will at some point explain to you what a battery management system does, but you also need to make sure that you're treating your battery well, that you know its current state, temperature, state of charge, et cetera, et cetera. Now, if the vehicle is hybrid, guess what? You also have an engine controller, okay? And then you have a transmission. So the overall complex of managing the electric drive, the battery management system, the internal combustion engine, the transmission shifting, and other accessories and everything else is what we call the supervisory controller, which manages the flow of power and therefore the energy of all of these different devices that interact with one another so that you can arrive at an optimal energy usage in your vehicle. And that's what this class is about. Eventually, we get to that point. So that's the big picture. Let's take a look at the Toyota Prius inverter. Why not? Okay. So how many electric machines do I have in the Toyota hybrid system? I have two, right? MG1 and MG2. So I'm going to need two inverters. So what you see here is that you have an inverter. How many switches? 6. How many diodes? 6. Okay. And then you have another inverter. One for MG1, the other one for MG2. Do you know what these strange symbols are? I put like a circle around the wire. What do you think that means? Could it be a current sensor? Does that make sense? So if you haven't seen it before, that's a current sensor. A symbol. Okay. And how many currents are we measuring? 2 of the 3, because the third one is automatically determined from the other 2. So save a sensor. There's another device here. So far, so good. There are 2. Yes, question. Push the button if you don't mind, or hold it. Touch and hold until you see the red light.
So aren't we actually making the current, all the 3 currents, like equally phase difference, like 120 degrees apart? Because that's what usually.
So you want to create the currents equal to one another, but the world is an imperfect place, so you better measure. Okay. So you make a good point. I mean, in theory, we know what those currents are. But remember, you have a feedback loop. You're trying to do feedback control. You better measure them. And the truth is that nothing is ever perfectly balanced and perfectly equal, right? That's the inverter. Then there is another device. So here's my inverter. There is another device called the boost converter. The boost converter is, in fact, a DC to DC converter. Okay, and this DC to DC converter is called the boost converter because it boosts the voltage up. There is also something called the buck converter that bucks the voltage down, okay? And guess what? If you're willing to put all of the components in the same system, you can make a buck boost converter that will allow you to decide whether you want the voltage to go up or down. In this case, Toyota only needed a boost converter, and the boost converter requires an inductor and a couple of switches. Now, if you really want to know how a boost converter works, go to my book, and let's make sure that the chapters on power electronics and electric machines are contained in the website. I forget if it's chapter 12 or 13, the power electronics one, but there's a power electronics chapter in my book that explains how buck and boost converters work. It's actually not that difficult to understand, but they're nonlinear, so it's not immediately intuitive. Okay. And that's the DC to DC converter. Okay, and what it says here, DC-DC converter, AC inverter, these are the controllers that manage all of those things. That's enough, good enough of that. So, let us show an example. And this example is going to push you a little bit, but it's going to also explain some useful things. First of all, remember I explained how Gen 1 of the Toyota system had slabs of permanent magnet material, and Gen 2 had something that was more like a V shape. In an electric machine, you're going to have to now listen to my words and one more time believe me, so to speak. But I'm convincing. You'll believe me. In an electric machine, you can generate torque from 2 fundamental processes. One is magnetic torque. So if I put permanent magnet in here, that's going to generate a torque. We call that the permanent magnet torque. And if I have a simple geometry, okay, a simple geometry like that, all I have is permanent magnet torque. However, there is another torque that is called reluctance torque, which has to do with the asymmetry in the machine, in the rotor. And this reluctance torque, see, remember I talked about the d-axis and the q-axis? Direct axis, quadrature axis. They're virtual, okay, but they are very important. The inductance, it's as if you had a two-phase machine, okay? The inductance of the D phase and the inductance of the Q phase are very similar to one another. The difference is pretty close to zero when you have a machine that has the symmetrical even spacing of the permanent magnets. When you have a V-shaped magnet insert in this machine, now you have an asymmetry in the reluctance of the machine, and that's basically says that in one of there's two fundamental inductances, and one of them is different from the other because of this asymmetry. I'll just show this graphically, but look at it this way. The torque produced by this machine under field-oriented control, in this DQ axis control, the torque T sub E has a permanent magnet component, which is proportional to the Q current. And it has a reluctance torque that is proportional to the product of ID times IQ. But this component is multiplied by the difference between LD and LQ. So in the Gen 1 electric machine, there is no reluctance torque. In the Gen 2, on the other hand, you have both the PM torque and the reluctance torque. So here's what happens. This is now going to hopefully make sense. Gen 1 only has blue, the reluctance torque. That's what it looks like over 180 degrees. The reluctance torque in the net is equal to zero, because whatever you gain at some point, you'll give away at another point, because you can't make work out of nothing. But the reluctance torque, this is what's important. It has a net value of zero, but it has oscillations. And here is the key. When you add the reluctance torque to the permanent magnet torque, your peak torque increases. So the area under the curve will be the same, but you're going to get a higher peak torque. This is actually the reason why. Now I'm going to jump back real fast because I showed you a picture of the Toyota Prius. Oh, darn, it was in the other lecture, but it's worth going back to it. I'm going to go back to lecture 9 and show you there was a key picture. If PowerPoint allows me. No, not here. Here it is. That's the one that I wanted to show you. So that difference that I showed you in lecture 9 between the original Toyota hybrid system and the second generation, this difference in torque comes from the presence of that reluctance torque. Could it be that they also had more powerful permanent magnets? Sure, that's possible too. I don't know all the details of their design. But that's an important consideration that I really wanted to make. Now that we're here, let's go back to where we were. We were here. So now that I've explained the fact that the presence of this reluctance torque can give you additional torque. I can also show you that this Park and Clark transformation, and if you want to know how you make this transformation, basically you go from IA, IB, IC, IC, through a trigonometric transformation, you're going to go to the two, which are going to be ID and IQ. I0 is there, it's unimportant. I0 doesn't do anything. You do it so that when you invert that matrix, it's a 3 by 3, and you can invert it, actually. That's all. That's just for convenience. And then later, you're going to do ID and IQ, and you're going to convert them again to IA, IB, and IC. Okay, so those are the transformations. Then, when you have done that, and you are now in this DQ domain, it's as if you had two circuits, two phases. They're virtual. Physically, you have three, okay? But you have two virtual phases called D and Q. Each of them is a winding. And each of them being a winding means that it's going to have some inductance, some resistance, and guess what? A back EMF. So what you really have is two differential equations that describe the relationship, dynamic relationship between voltage and current. And take a look at this. VD is equal to RID plus LD DIDT. So far, so good. And then you've got the back EMF, and what the back EMF does is it brings in IQ. It couples one circuit to the other. So then when you go to VQ, you have RIQ, LQ, DIQ, DT, and now you couple this to ID, and on top of that, you have the flux from the permanent magnets. That appears in that equation. And the torque, I showed you the expression before, okay? So these are the differential equations, nonlinear, that describe this basic configuration of a PM synchronous machine similar to the one Toyota uses in the hybrid system. Now, yes, sir?
Sir, why is the back EMF and VQ, like they are of different signs? It should be...
So you have two different, say that again?
VD and VQ, we have the back EMF of different signs. One is negative and other is positive.
Yeah, that's a good question, and I'm not quite sure. I'd have to think about that. I don't have that question. Do you come to CAR? Are you a CAR at any point in time? No? No, because there is a person who could answer your question instantaneously. Anyways, I'll try to remember to bring you deserve an answer. I just don't have it off the top of my head. This is the back EMF the way we've always thought about it, and you notice that there is one caused by the permanent magnet and one caused by the reluctance term. You know, my instinct would be to say, no, I think that should be like that, but I know who prepared this slide, and I need to ask her, okay? So, bottom line then is that the dynamics of this system are described by two first-order ordinary differential equations that are nonlinear, and then your output equation is the torque. Yes, you're right.
So in this kind of motor, I have an asymmetrical torque curve, which is in crank angle domain. Crank angle domain of the electric motor. Does that mean that I need to have something to balance the motor shafts, just like we do in crankshafts?
In a three-phase machine, that's a good question, the question about balancing. A three-phase machine is, if the three-phase currents are properly spaced phase-wise, is inherently balanced. So you don't have to worry about that. Now, here's what's really important. You have a space vector model. Well, forget the word space vector, I haven't explained that, but here's what I wanted to point out here. The model looks pretty simple, except for the fact that LD and LQ are not constant. Those maps describe LD and LQ as a function of IQ and ID. In other words, what inductance you see is related to the currents you have in the machine. So a seemingly innocent model, okay, in fact, is actually more complex than that because of the electromagnetics of the machine. It's pretty complicated. And I think we've already talked enough about losses. I don't need to say more about that. The same idea of electrical losses, mechanical losses, and core losses applies. And in the rest of this lecture, there are some pictures on some testing done of an electric machine. And I just want to point out that by changing the switching strategy, you can change the losses in the machine by a few percentage points. So if you're interested in improving the efficiency of the machine to reduce the heat that it generates, the difference between 2.5% and 3.5% is significant. Let me explain why. This was done for the Buckeye bullet. So those machines, two of them are operated at, it says 200 kilowatts, but they're operated at 2.5 times the rating, so 500 kilowatts. Two of them are 1 megawatt. Is 1% of 1 megawatt a significant amount of heat? You bet it is. So if you can reduce the heat by 1%, that helps your cooling system a lot. So those are some of the studies done in this study, in these, and I am just not going to go any further into detail, also because these things are more complicated than is appropriate for this class. Some of you may choose to read that stuff on your own, and then you can ask me some questions. Unfortunately, we got behind because of the equipment malfunction last time, and I'm not capable of completely finishing everything. So we'll just carry this little bit that is left, and I don't believe it's that many slides. I'll talk about the EVT again. Yeah, it's probably about 8 or 10 slides. I will do it at the beginning of the next lecture. So thank you very much. Enjoy the weekend, and I will see you in the next lecture.